So let's take a look at this one. What's up? Yeah. So looking at this one, which pieces do we have? A, B, H, or K?
A and B.
A and B.
Shit.
No H, no K. So there's a couple ones with 6, 7, 10. So what is our A? -1. So there we go, adjusting my pens. So A equals -1. What is my B?
0.
2. B is multiplied against X and inside our special function. B is our new one and weird.
You're right.
So we don't have any H, there's nothing added against the X inside the special function, and there's no K, there's nothing added on the end. So we're gonna start this the same way we did yesterday, where we put our absolute value parent function in the middle. So I'm gonna make my giant table, and I put my parent in the center. So this is my X and Y, my parent being my Y equals absolute value of X. That's the parent function. It has no A, no H, no K, no B, no nobody. Just the Y and the X. That's our parent function. Our good view of the center are -2, -1, 0, 1, and 2. We pick those X's because they're a good view of the middle. And our Y values go through our parent function to get there. So that's just our super fast review of how we fill in our parent table. Questions on that part? Because the way I do my transformations is I do them to the outside. This is not the only way you can do it. A lot of people like them in 2 separate tables, and that's totally fine. I just feel like this keeps things way more organized on the screen, which is why I do it this way. But so what we're going to do is we're going to take our X's and our Y's and apply our transformations. For our Y's, it's exactly the same way we did as in Algebra 2. We take our Y times our A plus our K. For our X's, this is where we have our funky thing because we have a B. So we have our 1 over B times X plus H. Because B is weird and it turns everything on its head. So we multiply by the reciprocal of B. So when I substitute in my actual A and B values, we're going to take our Y's times our -1 plus 0. We don't have any K. And we're going to take our X's times what? 1/2. 1 over B. If B is a fraction, I highly recommend you simplify your fraction of a fraction before you try and put it through the table. But when B is a whole number, this is fine. Yes, Jane. I cannot guarantee that. They're not going to be tons because I'm not that mean, but in the book there could be. But I'll never make you calculate one on a quiz without a calculator because that's just mean. All right, so we're going to do these transformations. Get a color we're not using. This is one. So I'm going to take my -2 times 1/2. And what are we going to get? What is -2 times 1/2? -1. Taking my -1 times 1/2. -1/2. 0 times our 1/2. 0. 1 times 1/2. And 2 times 1/2. 1. For my Y's, we're multiplying by that -1. So 2 times -1. -2. 1 times -1 is -1. 0 times -1 is, just 0 still. 1 times -1 is -1, and 2 times -1 is -2. These are my x's, and these are my y's. These are the points for plotting. So -1, -2. Should we change my color? There we go. -1, -2. -1/2, -1. So right there. 0, 0. 1/2, -1, and 1, -2. Absolute values are made up of straight lines, so use a ruler. There should be plenty of rulers out, but if you need one, I've got bunches up here. Absolute values are V-shaped, not U-shaped, so they are made of straight lines. Anytime we have something with a straight line, please use a ruler. Yes, I can tell. And always draw to the edges of your graphs. It makes it so much easier to read. So we can look back and look through our transformations. Our A of -1 gave us a reflection over that x-axis. That's what made it upside down. And our B of +2 is a horizontal compression. So it's been squished this way, which makes it skinny and long. So it's a horizontal compression and a vertical reflection. Horizontal compression. It's been squished. Like if I took my parent function and came to this side and squished it in, it made it smaller and skinnier. So it's a horizontal compression. Okay, so we worked yesterday with parabolas, x squareds. We worked with absolute values. Questions on either of those two? We just only did one absolute value yesterday, so I wanted to make sure we did another one. Okay, because we're going to do a whole bunch of other kinds of functions today. Need more time on this one? Okay, giving you a second. All right, you ready? Because the next one we're going to do is a cubic. Yay, cubics! Yeah. Is okay for with these sometimes. I pay nothing for them. So they exactly live up to what I pay. I don't get this from a supply closet. All right, so our first piece here, we've got our f of x equals 1/2 times the quantity of the opposite of x cubed plus 1. So we're going to start the exact same way. We're going to see what our a, b, h, k, all those guys are. So what do we have for a? A is 1/2. How about for b? -1. Right? -1 times the x. We're never going to have a variable inside our a, b, h, or k. Like never ever. How about our h? What do we have for h? 0. There's nothing added or subtracted to the x in there. How about our k? 1. So this time we're working with a cube, so we're going to have a new parent function. So my x and y in the middle of my parent function, that's my y equals the basicest of basic, no a, no h, no k, no b, just x cubed. This is my parent. We use that to figure out everything else. So it's really important that we pay attention to that parent function. For our x's, we can keep using the same ones. There's nothing special about cubes. I want that good view of the middle. So I'm going to take my -2, -1, 0, 1, and 2. What are my y values going to be here for my parent function? Ooh, careful, careful, careful. -8. Not 4. -1, 0, 1, and 8. So as we're on a new function, I'm going to sketch our parent function in just so we can see it. You do not have to do this, but I just want us to see what it looks like so that we can see our transformations. So our parent function looks kind of like this. Again, you do not have to draw the parent function in. I just want us to be able to see it when we're looking at these transformations so we can see what's happening. Okay? We are going to do the exact same steps as we've done for all the others to graph these transformations. We will take our y times a plus k, just like we've done since Algebra 2. And we're going to take our x's times our 1 over b, or 1 over bx, I don't care what order it is, plus h. So we're going to take our x's times what for this one? Times -1. 1 over -1 is the exact same thing as -1. So it's just kind of easier to think of it as -1. Plus h, so we're not adding anything, so I don't need to write that down. Hello, screen. Are you back? What's that? There we go. We don't need to add 0 because it doesn't change anything, but you can write it if you want to. So for our y's, we're going to take our y's from our parent function times our a. So we're going to go times 1/2 plus k. So we're going to go plus k plus 1. So we're going to take our x's times -1/2, or times -1, excuse me. So that's going to give me a +2, a +1, 0, -1, and -2. This gives us a reflection across the y-axis. It rotates it this way. That negative sign on our b gives us a vertical rotation, or a horizontal reflection. So for my y's, -8 times 1/2 gives me -4, plus 1 gives me -3. -1 times 1/2 is -1/2, plus 1, it gives me +1/2. 0 times 1/2 is 0, plus 1 is 1. That one's easy peasy. Yep, the next one's going to be 1.5 or 1.5, and I genuinely do not care if you put these as fractions or decimals. Whatever works better for your brain. It makes absolutely no difference. 1.5 and 1.5 are exactly the same thing. I do not recommend doing unsimplified fractions, like 3/2 is a lot harder to quickly graph than 1.5 or 1.5. There's not anything wrong with it. Technically, it's correct. 3/2 is fine. It's just harder to work with. Yes, Julie? -1 times 1/2 will give me -1/2. -1/2 plus 1.
Oh, right.
So don't forget our plus 1. All right, so then our last one here, what are we going to have? 5. Because 8 times 1/2 is 4, plus 1 gives me 5. So we're going to plot up our points. We've got our 2, -3. 1, 1/2. So it feels like we're going the wrong direction. 0, 1.5. -1. Oh, sorry, 0, 1. I was reading my table wrong. -1, 1.5. And -2, 5. So it's a cube, so it's a curve, so we don't need to use a ruler. But we do want to go all the way to the edges. And we can see that this has been compressed. My A is small, so it's made it squished. That curve in the middle is where we can see that. We've got that B of -1, so we have that reflection across our y-axis. It rotated this way. It's not had any horizontal shift, but it did shift up 1. That horizontal shift we see best at this center point, which will actually always be here for any of our symmetric functions that are going to give us an h, comma, k, kind of like a vertex, kind of like parent function of parabolas. That hk will always be in our table somewhere. Most of the time it's going to be in the middle. For everything except square roots, it'll be in the middle, really. All right, questions on our first cube? Okay, we're going to practice another one. Because I'm not just going to have us do one. Boop. So our next cube is a little bit more normal. If that was a 2 as a power, we'd be significantly happier. It's going to be a parabola and so much more familiar. But it's a cube. But it's x minus 4 quantity cubed plus 2. So what transformations do we have here? Just h and k. So what is my h? 4. What is my k? 2. So how is this going to be moved? Right? 4 up 2. We're still going to do the exact same process. I'm going to take my transformation table. I'm going to put my parent in the middle. It's going to be the same parent we used on the last one for my y equals x cubed. Because it's always whatever it is as our function without any really other numbers other than exponents in it. So we still want that good view of the middle where we take our -2, -1, 0, 1, and 2, giving us y values of -8, -1, 0, 1, and 8. So it's really, really important that we get that parent table correct. It's really important because we're applying our transformations to that table. So slow down when you're filling in your parent tables, because if we get that wrong, it has an effect on everything else. So since I don't have a B, yes dear? For everything except square roots. We'll talk about square roots when we get there and why we want something different. Okay, so these are always a safe bet, and you can write them on square roots. They're just going to make your life real hard. So since I don't have a B, I'm not even going to write it down. I'm just going to take my x plus h and my y times a plus k. If I don't have a B, I'm not going to write it down because he's gross. If you want to, you can. It's our 1 over b. But I don't like him. He's not very nice. He's kind of icky. So I'm not going to write it down. So we're just going to add our h to our x's. So we're going to add 4. So what is my x column going to be now? 4, 5, and 6. For my y's, we're going to go times our a. Our a is 1. We don't have an a. So we're just adding 2 really here. So my y's plus 2. -6. 1, 2, 3, 10. So again, some of these are going to be off the graph. This one will just barely fit on the unnumbered if you grab them, but if you grab the number one, that There's not a chance of that 610 fitting. So if it doesn't fit, just draw yourself a little arrow up on that top of that axis so you know that there's a point way up there. But we're going to plot up these points. So I've got 2, -6, which on the numbered graphs will be right at the very bottom. 3, 1, 4, 2, 5, 3, and then 6, 10. Which again, if you have the numbered graphs, just draw yourself a little arrow kind of right there, and that'll let you connect it up and still have it look right. Because it should look kind of like that. And we want to make sure we go from edge to edge on our graph. Please stop drawing me tiny little graphs like this and expecting me to figure out what the heck you meant. Do not draw teeny tiny babies like that.
Big graphs.
That's bad. This is good. Big graphs are good. Little graphs are bad. Draw big graphs. Okay? Questions on our cubes? It's a very similar vibe. So then let's think about our square roots. Oh my gosh. I know it's so much. Told you all we'd be graphing all day.
I love graphing.
Well, good. We're going to graph tomorrow too.
Oh,
There's a lot of graphing in this one. This one's all about graphs because we're working our way up to piecewises. What's up? Whatever you want to with it. I was like, I also have tons of paper if you ever want to do it like loosely style. All right. So what is our A? -4. What's our B? 1. So we don't even need to worry about him too much. What's our H? -2. And what's our K? -3. Lots of negatives here, so we're just going to be careful with that. So now I'm going to put my parent table in the middle, and this is the one we have to be super careful on. Because when we're graphing these, we are only thinking about real numbers. So our parent function is the one that has like no A, no H, no K. So it's just going to be our y equals the square root of x. No A, no H, no K. Nobody else. So since I'm taking the square root of my x's, do we need to have negative numbers? Because if we have negatives under my radical, what are they? Imaginary. We are not graphing imaginary numbers. This is not imaginary graphing. That is a thing, but this is not it. That's what my grad course is all about. So, since we're taking square roots and we can't have negatives, what x's should we pick for our parent table? 0, 1, 9, 16. We are rarely going to have, I missed 4. I'm like, that feels wrong. 4, 9, 16. Very rarely will we have a graph where we can even fit 16 on it. You can put it there if it helps you see things or if we like that symmetry of having 5 things. But very rarely will we ever have a graph that fits that. So what are our y values going to be? 0, 1, 2, 3, 4. That's why we picked them. This is really our only one where we have different x values, simply because square roots, if I did 1 and 2, those would be really gross. Or at least square root of 2 is gross decimally. Square root of 3 is gross and decimally, and it wouldn't really help us see what's happening. So the transformations happen exactly the same way. I'm still going to take my y times my a plus my k. We're still going to take our x times 1 over b if we've got it, plus h. So we're taking our x's. I don't have a b in this case, so all we're doing is subtracting 2. And for my y's, we're going to multiply by our a, so we're timesing by -4, and then adding k, plus -3, -3. This is one of those reasons we do our transformation form, is because this calculation is way easier to do than trying to do a plug and chug into that square root. So if I take my x's and we subtract 2, what are we going to get as our transformed x's? -2, -1, 2, 7, and 14. So we're clearly not going to be able to fit that 14 on our graph, but we're still going to practice it because it's good practice for us. So our y's, we're taking our y's times -4 and then -3. So 0 times -4 is just 0, -3, -3. 1 times -4 -3, -7. 2 times -4, 2 times -4, -3, -11. I know, you just jumped ahead of me, and I said 2 times -4, and we said -11, and we all just kind of went, oh. All right, and so clearly none of the rest of these are going to wind up being on my graph. You can fill them in as your heart desires. We'll wind up with -15 and -19. But those ones will clearly not fit on my graph. I'm going to sketch in our parent function so that we can see what that looks like, just because I didn't do that yet. 2, 4, 9, 3. So our parent function looks like this. So when we plot up our transformed function, we'll see those transformations. I've got my -2, -3, -1, -7, 2, -11 is just barely off my graph down here. I'm going to grab a white pen just so we can see it right down there. And then, zoom, off we go. So my graph is going to look like this, which we can just do an arrow there. If you want to go off the graph, you can. If you guys ever want graph paper to keep going or do bigger graphs, I have that too. But it's going to look like this. So we can see that it's had that reflection across our x-axis since our a is negative. It's been stretched pretty dang far. It's gone left 2 and down 3. So the transformations still occur in the same kind of way. It's just our parent table that's different here. Questions on this one? Okay, let's do another one. Let's do another one. Here we've got our square root of 1/3 times the quantity x minus 1 plus 2. That is how our b's are going to be put when we also have an h. They are outside the quantity. There you go. Then I threw it back on the floor. Okay, same process. Same process. So what is our A here? 1. What is our B? 1/3. What is our H? Careful. +1. H always has the opposite sign of its expression. Always, always, always. How about our K? 2. K stays the same. H is the opposite. For those of you that had Miss Hannah, she said the opposite a lot. I think she did. That's what people used to tell me. I don't know. I never get to talk to her. She's on the side of the building. Okay, so we're going to use that same parent function from the last one. Boop. Because it's a square root, our parent function is our y equals the square root of x. That's our parent. Whatever our function is without any other numbers, that's our parent. So we pick our x's to find our y's. Since we're working with square roots, we're going to pick those perfect squares of 0, 1, 4, and 9. I'm just going to do the 4 because almost never will the others wind up on the graph. And our y's give us our 0, 1, 2, and 3. That's my parent. I'm not going to graph it this time. I'm just going to use it. So we're going to do our transformations to the outside. What's up? Mm-hmm. Without any A, H, K, or B.
So you just like ignore everything else?
Yes. That's how we find the parent. That's our starting position. And then we apply our transformations. So just like on, I'm going to flip page here for a second, on our cube, our parent was this without any H or K. It was just y to the x cubed. Just like on our absolute value, our parent function was y equals the absolute value of x. No negative, no minus 2. So here we have our square root of x. So doing these transformations, we're going to have our y times a plus k. And our x's, we have x times 1 over b plus h. So I'm going to do the 1 over b off to the side because I don't like fractions of fractions. 1 over 1/3. That's what 1 over b is going to be. How could I rewrite that? Yeah, this is 1 times the reciprocal of what we divide by. 3 over 1. This is our keep, change, flip, if that helps. Keep the 1, change the sign, multiply, flip by it. So it's the same thing as multiplying by 3. So this is going to take our x's times 3 plus our h plus 1. So our 1 over b, just to connect it up, that's what we did up here, just so that we could see it. And for our y's, we're taking our y's times our a, which is 1, so that's not actually doing anything, plus k, plus 2. So we're going to take our x's times 3 plus 1. So 0 times 3 is 0, plus 1 is 1. 1 times 3 plus 1, 4. Ooh, wrong color.
Oh, because we switched, right?
What's up?
With B, because like we flipped it, right?
Yes, because we multiply by 1 over b, so it was 1 over 1/3, which is gross. So we fixed it. So then we have our 4 times 3, which is 12, plus 1, 13. And 9 times 3 plus 1 is 28. Which is why we don't tend to go too far out on our square roots, because they get real big real fast. So for our y's, we're just adding 2. We like that one. 0 plus 2 is just 2. 1 plus 2 is 3. 2 plus 2 is 4. And 3 plus 2 is 5. I ask such hard questions sometimes. All right, so let's plot those up. 1, 2. 4, 3. 13, 4. So I know at 4 we're going to have a point way over there. And that's kind of all I can fit on my graph. Even with the big ones, I know that there's one at 4 over there. And our square roots are going to look kind of like this. So this one is very, very, very vertically compressed. Squish. Or it's horizontally stretched. Does the same thing. Okay, questions on square roots? Because we gonna do another one. Yes. Yeah. Look at that. You did these. You've done these. You have. We spent a whole chapter on these in Algebra 2. Really, really. 1 over x is our parent function. So these are our rationals. When we have these, our transformation form, for those of us that don't remember, that's our a over b x minus h plus k. That's our transformation form for this. So what transformation do we have? A. All we have is an A. All we have is a vertical stretch. So let's remember our parent function first. We're going to put our parent in the middle. And our parent is the basicest of basic with nothing over it. So y equals 1 over x. So we're going to, again, we're not in square roots. So we're again picking that good section of the middle. -2, -1, 0, 1, and 2. What are my y's going to be? -1/2, -1, careful, undefined, this is going to be an asymptote. So we're going to have our infinite discontinuities showing up. Oh my gosh. It's the dotted line. It's the walls we can't crash through. All right, how about the rest of our y's? 1 and 1/2. So I'm going to sketch this out so we can remember what this looks like. So our -2, -1/2, -1, -1. We have an asymptote at 0. It can't cross it. I'm going to put a pink line here. Ooh, that's almost impossible to see. Hang on. There we go. That's better. And then I have my 1, 1, 2, 1/2. So when we're in our rational functions, we also have a horizontal asymptote because our negative x values will never give me a positive y. So this also has an asymptote this way. So our parent function looks like this. Told you you've seen these before. So when we're doing our transformation here, almost, I still got 2 minutes. We still do the same thing. X times 1 over b, which we don't have any of, plus h, which we don't have any of. I'm going to take my y times a plus k. I do have an a this time, so we're going to take our y times 2. So our y's are going to be -1, -2, 2, and 1. So if we're looking at our transformations here, just because I know y'all are packing up, I'm still finishing it. -2, -1, -1, -2. So we didn't have any horizontal shift at all. So our asymptotes stayed the same. which is why I can do this all right here. So this had our vertical stretch with that A. So we will work more with these. I will show you that greatest integer function, and then tomorrow we're also going to work with piecewise functions.
Better than the first part.
Huh? Oh yeah?